Good afternoon, everyone. Welcome to today's webinar on mathematical design of soft magnetic materials, hosted by IEEE Magnetic Society's Santa Clara Valley chapter. IEEE Magnetic Society is a premier organization for professionals in magnetics research and technology, covering almost full spectrum from basic knowledge in magnetism to applications, including technologies in spintronics, magnetic recording technology, magnetism for energy, motors and actuators, and magnetism for health. With about 3,000 members in 46 chapters located in 22 countries, the IEEE Magnetic Society hosts flagship conferences and journals. We provide our student members with summer school program. We provide our members with conference discounts, free books and publications. We provide great networking opportunities for professionals. We also have a very strong distinguished lecturer program in our society. Located in the Santa Clara Valley, our local chapter is in line with the IEEE Magnetic Society's objective of being scientific, literary, and educational. We host monthly invited talks from experts in both industry and academia. Today, we are very glad to invite Professor Balakrishna from University of Southern California to present her recent study of mathematical design of soft magnetic materials. Dr. Balakrishna obtained her PhD program from PhD degree, from University of Oxford. She was a postdoc research fellow in the University of Minnesota and MIT before she joined the University of Southern California. Before I turn the floor to Dr. Balakrishna, I would like to remind all the participants, please keep your video off and the microphone unmuted during the presentation. At the end of the presentation, you can raise your hand to ask your questions by click the raise hand in the reaction button on the bottom right of your screen. And then we will be able to see that you raise your hand, and we will ask you to turn on your microphone to ask your questions. With that, please help me to welcome Dr. Balakrishna for her presentation of mathematical design of soft magnetic materials. Now, Dr. Balakrishna, you may share your screen.
Thank you very much, Min, for the very kind introduction, and I'm very delighted to be here and share my work with you all today. So I'll start with sharing my screen. Okay. Yeah, so please feel free to interrupt me anytime during the talk. You can raise your hand and I can take any questions. Given that we're not a very big audience, it would be very nice to have a more interactive session as well. So I'm an assistant professor in the mechanical engineering department at USC, and I started to work here nearly for almost 2 years to this fall. And the work I'm presenting today is how we use certain mathematical models to identify design principles that can make soft magnets better. Specifically, the central thesis of the kind of research that we do is, let's see if I can get my pointer out. Yeah, the central thesis of the kind of the work that we do is we identify how fundamental material constants, these could be magnetic material constants, or these could be, in case of other phase transformation materials, lattice geometries, how they affect the microstructures that form in these materials, and how these microstructures in turn affect physical properties. So when we're thinking of soft magnets, we're thinking of something like magnetic hysteresis. And we use models to understand the interplay across these different levels. And the additional step that we do in here is once we identify how these parameters and microstructures affect properties, we're interested in going back to identify how we can tune the alloy composition or how we can change certain material constants by doping or alloying, so we can engineer better properties in terms of like hysteresis. The work that I present today has been done together with my student, Nega Ahani, and my former collaborator, Dick James from the University of Minnesota. The talk today has 2 lines. I'll primarily be focusing on the first line of research, in which we try and understand how microstructural instabilities, during the talk, I'll tell you what I mean by that, and how material constants shape magnetic hysteresis. And if time permits, towards the end, I'll give a very brief overview of how we are working on crystallographically engineering some of the magnetic alloys to mitigate features like fatigue, to enhance their reversible cycling between the paramagnetic and ferromagnetic phases. Okay, so I'll start with the first line of work, which essentially focuses on a concept which I guess is quite familiar to many of us in the audience today, is that on magnetic hysteresis. So when we look at several applications of soft magnets, whether they're used in spintronic memory devices or those that go into wind turbines, they're even in fact used in induction motors, these soft magnets kind of find themselves as potential candidates, not just for sustainable energy conversion, but also for rapid energy conversion. They can very quickly switch between the magnetized, demagnetized states, or even their polarity of magnetization with very minimum applied external field. So what that looks like is if we just take a simple hysteresis loop. So here we have the applied field that's denoted by H, and the magnetization, the average magnetization in your material, that's denoted by M. And here you see some schematics of the magnetization in your body. And you apply an external field, you switch the magnetization, and it traces out this characteristic hysteresis loop. And the force, the external field at which the magnetization reduces to 0, or the average magnetization in the system is 0, we call that coercive force or coercivity. And the width of the loop is what I would be referring to in this talk as the hysteresis width. So soft magnets are magnets that have very narrow hysteresis width. That is, you need a very minimum external field to switch the magnetization, and this is characterized by a very small hysteresis width. And so in the magnetic alloy development community, as well as the metallurgic community, one way in which you can develop soft magnets that have, for example, crystalline or long-range order, is to change the alloy composition so you can tune one material constant, which is called the anisotropy constant, close to 0. So I'll talk more about this anisotropy constant later on in the slides, but for now, essentially what this anisotropy constant does is it's the penalty you pay when you try to rotate the magnetization away from the easy axis. So if you make the value of this constant close to 0, you should be able to switch the magnetization from one direction to the other with very minimum external load or external field. So when we're developing these soft magnets in the community today, the common strategy is to change or tune its alloy composition so you can tailor this anisotropy constant to be as small as possible or as 0 as possible, because the larger it is, the idea is it generates these kind of hard magnets, which have other applications. But this actually has led to certain outliers, and I'll start with a classic example, which is the Permalloy problem. And this is one of the long-standing problems. It's essentially what the few of the researchers in the Bell Labs in the 1950s, the names of which are given here, Bozolt and Walker, what they did was they wanted to find a soft magnet which had the smallest hysteresis, right? The smallest hysteresis width. And so what they did was they decided to alloy iron and nickel in different compositions. So what you see on the x-axis is different percentage of nickel that was mixed with iron. And then they made each of these specimens as kind of discs or pellets, and they measured their hysteresis or their coercivity. And what you see on the y-axis is a measurement which is called permeability, which is inversely related to your coercivity. So what that means is if you see a peak on this plot, which shows the highest permeability, it means that is the composition that has the smallest hysteresis. And so what they found was, based on the percentage of nickel that's present in iron, you can have magnetic alloys that show a range of these coercivities. And the softest magnet they identified was at 78.5% nickel content. That's a composition that today we call as the Permalloy. And this composition is one of the well-known soft magnets that's technologically relevant and important today. And so the question that they asked was, why exactly is this composition giving you the smallest hysteresis? And so what they did was, each of the specimens that they made, they went and measured the fundamental material constants. And what they found is kind of surprising, and I'll tell you why. Because the softest magnet, which is at 78.5% nickel content, when they measured its fundamental material constant, they found that the anisotropy constant for this is actually not zero. The anisotropy constant, in fact, goes to zero at a composition of 75%, but that is not the magnetic alloy that shows the largest permeability or the smallest hysteresis. In fact, you see the smallest hysteresis at a composition where your fundamental material, where your anisotropy constant is not zero. And another interesting feature was they saw a second peak in this curve, which is the 45% 45% nickel in iron, which is also one of the soft magnets. But in fact, the anisotropy constant of this composition is very large. So it goes back to us questioning the fact that is the idea of just changing the anisotropy constant close to zero, is that the only way, or is that the primary or the dominant factor that's controlling the width of your hysteresis loop? And this is an example of an outlier which shows there are some gaps in our understanding on how we think of magnetic hysteresis and whether this constant is the primary role. Because if you think of a magnet, they have other material constants, and briefly touch on them when I come to the modeling side of things. You have some things called magnetostriction constant, you have something called a saturation magnetization, and all of them we suspect play a role involved in this magnetization reversal. While anisotropy could be playing an important one, we believe that the reason why you see certain peaks at which anisotropy constant, or we hypothesize at which they're not zero, is because it's a delicate interplay between the variety of these constants. And you see similar outliers in literature. So, for example, if you think of nickel, manganese, gallium, it's one of the examples of a soft magnet along specific crystallographic directions. It has a very small hysteresis width, despite of having a very large anisotropy constant. And here is another figure from the Permalloy problem that shows that the hysteresis or the coercive force is minimum at 78.5%, but your anisotropy goes to zero at other values. So this makes us rethink as to how we compute hysteresis and whether this material constant is the only parameter that plays an important role in this reversal. And so what we do in this kind of a project is to start from a well-established theory called the micromagnetics theory that started with William Fuller Brown quite some time ago. It's a very well rigorously developed theory. I say rigorous because it's one of the theories wherein you have a very well-defined energy terms where each of these coefficients directly correspond to a measured material property rather than us fitting a curve to any specific parameters. And this theory has been quite well applied and shown to work very well for other magnetic materials, or for other magnetic properties, whether it's in terms of actuation or in terms of microstructure prediction. So this theory is kind of very well tested and validated. So a characteristic or a distinguishing feature of this theory is it very neatly brings together the different energy terms that play a role in magnetization reversal, for example. So if you start with something called as the gradient energy, or well, if you start, for example, with something like the anisotropy energy, the constant that I was referring to, which plays an important role in this reversal. So here is a cartoon that shows a unit cell with 3 different crystallographic directions, and the blue arrow here is schematically indicating that this material likes to magnetize along one crystallographic direction. And so what the anisotropy constant does is the magnitude of this constant tells how much energy penalty is the material, how much energy penalty are we going to pay if we're trying to rotate this magnetization away from what is called as its easy axis. And this energy penalty is quantified by this term. And you have other energy terms like the gradient energy term, which captures how the magnetization, which captures if the magnetization is rotating from one direction to another. In case of microstructure, what's the penalty that's introduced by introducing this kind of a diffuse interface where the magnetization has a gradient. And then you have is the elastic energy term. This is the energy term inside which your magnetostriction constants are buried. And essentially what that means is when you have a material that's, let's say, magnetized in a random orientation, and now you apply an external field, you're reorienting the magnetization to align with your applied field. And this reorientation of the magnetization is also coupled with some stretching of your material. So there's a strain that's coupled with this magnetization rotation. And that strain is what is quantified by magnetostriction. And you'll see some of these constants in the subscript have either 100 or 111. And what that means is that's the amount of strain that you generate when when the material stretches along specific crystallographic direction. So there's some elastic energy that is associated when your magnetization is being switched from one direction to the other. And this term, in fact, is often not included in several calculations because magnetostriction constants are quite small. They're measured in the order of microstrains. That's like 10⁻⁻⁶. So they're not suspected, and as well, rightly not suspected to play a major role in here. And then you have other energy terms. This is, for example, your external field. So when you have a magnet that's placed in an external field, and if the magnetization does not align with your applied field, the material experiences the torque so as to organize itself or rotate the magnetization and align itself with the applied field. And you also have an energy term that's called the demagnetization energy, which essentially is like a self field. When if you have a magnetized body, you have the poles of the magnetic body, that's the magnetization at two end corners, and this generates an external field which affects the microstructures that form in the material. So essentially, when you're applying an external field to the magnet to reverse its magnetization, it's an interplay between all of these energy terms, which allows this magnetization to switch from one direction to the other. And so what William Fuller Brown, who was also very puzzled or was very interested in the Permalloy problem, was he tried to apply this micromagnetics theory to predict hysteresis or to understand if we can predict the coercive force for a given material. And so what he did in one of his early studies was to do a linear stability analysis of this energy term. Essentially, what that means is you write this energy expression. You start with an ellipsoid, a large ellipsoid body. Ellipsoid is one of these geometries that minimizes your demagnetization field and is also quite elegantly incorporated in analytical calculations. And so you start with a body that's uniformly magnetized in one direction, and you apply an external field, and you identify at what value of your external field is your magnetization going to switch. And when he did a linear stability analysis of this using this micromagnetics expression, he neglected the magnetostriction terms to keep it, because they were not doing a major contribution. And what he said was, well, the external fields, which when it's proportional to the anisotropy constant and inversely proportional to your saturation magnetization, the magnetization flips from one direction to the other. So if you take, for example, for iron and you substitute its measured material constants, the linear stability analysis of the linear approximation of the micromagnetics theory gives you a value of 500 Orsteds. But if you actually measure the coercive force for iron in an experiment, it's actually 3 orders of magnitude smaller. And so in his book, he described this as the coercivity paradox, which essentially means that doing a linear approximation of this well-established theory is not predicting the coercivity or the hysteresis width of these materials well. So there must be something that's kind of missing. And so, in fact, if you apply this approach of doing a linear approximation of this theory to predict hysteresis for the several of those nickel iron alloys they tested out in the Bell Labs, you would actually predict that the smallest hysteresis or the smallest coercivity would be for 75% iron nickel, for 75% alloy composition, and not at 78.5. And so that was also called as the Permalloy problem, because it wasn't clear why exactly is the 78.5% counterintuitive to the theoretical prediction is giving you the small coercivity. So what we do in our work is to rethink how we predict magnetic hysteresis. Well, so the linear stability analysis is failing in predicting the width of the hysteresis loop, but at the same hand, micromagnetics is a well-established theory. It's showing several of these phenomena, but somehow the linear approximation is not giving you the right picture of your coercive forces as well as the width of your hysteresis. And so we rethink about hysteresis in terms of what we call as nucleation barriers, and we think of it in terms of what we call as microstructural instabilities. And what I mean by that is, if you look through several of these micrographs of soft magnets, you often see defects in them. You often see, for example, here's an example of a pore defect in a soft magnetic alloy. And when you have a pore defect, this could be a non-magnetic inclusion. What happens is the material, to reduce its demagnetization field, it forms these kind of spike-like microstructures or a needle-like domain you see in many of them. And this microstructure is not something that's common, or is not something specific to this alloy, or it's not specific to just this defect. It's in fact quite it's quite ubiquitously found in several of these soft magnets. You see them at grain boundaries, you see them across near the edges and sharp corners. And here is a really nice book by experimentalists Hubert and Schaefer, who have developed very sophisticated microscopy techniques where they map these domains. And if you actually flip through this book, you'll notice several of these needle domains that surface in several of the micrographs, indicating that these are commonly observed across several of them. So what we think is, what we propose is, when we're computing hysteresis, we need to do a non-linear stability analysis in the presence of an instability or a large localized disturbance like that of a needle domain. Because when you're applying an external field across a microstructure such as this, these needle domains grow in size, and at a specific value, they completely reverse the net magnetization of the material. And the growth of this needle domain experiences a certain resistance, which is determined by the delicate interplay between material constants. And that's something that we want to, that is something that we propose to investigate. So that brings me to the three parts of my first line of work, wherein first I'll give you a bit more detail about the kind of model that we have developed, which is based on micromagnetics theory. But instead of a linear stability analysis, it does a non-linear stability calculation, and how this model can be used to predict hysteresis. And then we apply that to gain some insights into the Permalloy problem to see why exactly do we see minimum coercivity at a specific composition. And then we kind of, and then what we do in the last bit of the work, what we do, and something that's still ongoing today, is we apply this tool to see if we can identify certain mathematical relation between different material constants for which you can actually have soft magnets, or can we propose a design principle that can help that can help guide alloy development in which you can make really soft magnets. So the overview of the work is we use micromagnetics theory, which is when we simulate microstructures of hundreds of nanometers length scale and at diffusive time scales. But we are actually, in fact, predicting the hysteresis of a bulk magnetic material. If anyone's interested, I'm happy to explain what this theorem means. Essentially, it gives you a unique way in splitting your field, so you can actually model a very large bulk ellipsoid and predict the hysteresis of a bulk alloy, just to eliminate any of the shape effects that you can get by having a small microstructure. And then to this model, we are introducing a localized disturbance, which we model by a simple example of a needle domain or a spike domain. And we compute our evolution by using the Landau-Lifshitz-Gilbert equation. And we compute equilibrium conditions wherein we compute for the magnetostatic fields or the demagnetization fields, and we ensure this stress is equilibrated at every time step. Okay, so the key features of our work is we model a three-dimensional domain, which is about 250 nanometers in diameter, and you have a non-magnetic inclusion, and this which is at the center of this three-dimensional object. So the surfaces don't see the defect, but it's just a small pore-like defect that's placed at the geometric center. And so you form this kind of a needle domain that forms in one of the surfaces inside of your material, and you apply an external field. And this is how we are splitting the magnetization. So we're actually modeling a large ellipsoid. Let's see if we can get a figure. Yeah, so we're modeling a large ellipsoid where this domain is buried at the center. So when we predict the coercive force of a specific combination of constants, this is for a bulk alloy. And besides these two key features, we also decide to include elastic interactions in our model. However small the magnetostriction constant is, we're interested to see its effect in this magnetization reversal. You can find more details of this work in this paper, and I'm also happy to walk you through any of these aspects during the Q&A. Okay, so using this method, here's I can show you an example of a simulation of how it looks like. So this is the three-dimensional one. We're looking at a cross-section of it. I'm showing this to you in 2D, but the computation was 3D. So you uniformly magnetize it along one direction. So this is what you see. It's, let's say, placed over here with more or less a saturated magnetization there. And now what you do is you start to decrease the applied field in this direction, which causes your needle domain to grow. And as you lower the field and you switch to the opposite direction at a specific critical value, this needle domain grows abruptly and results in complete magnetization reversal. And that value of your external field is what we extract as the coercive force or the coercivity. And for iron, for example, we're able to predict that in the presence of a nonlinear disturbance or a localized disturbance, the coercivity is 5 oersteds. It's still an order of magnitude larger than what we see in experiments. And there could be reasons as to why we see that, because we assume a single crystal, we assume perfectly smooth interfaces, we just introduce one localized disturbance or a defect. But the positive side is this is giving 2 orders of magnitude a better prediction than the current methods that are used to predict coercivity or to measure magnetic hysteresis. So we use this framework to test if we can help understand the interplay between material constants when we think of the Permalloy problem. And so what we do is, so when Bozorth and Walker measured the different coercive forces as a function of nickel content in iron, they not only predicted the coercive force, but also measured its fundamental material constants. So its anisotropy constants, its magnetostriction constants, and each of these alloy compositions were measured, which serve as input to our model. And so when we do not include in our model the magnetoelastic interaction, or just model it as a function of the anisotropy energy, we see that the minima is actually at 75%. But if you include the magneto, so you can see in a zoomed up version, the minima is somewhere around 75%, which is where your anisotropy constant goes to 0. But if you introduce your magnetoelastic interaction, so your magnetostriction constants, the minima in fact shifts to that of 78.5%, as you can see over here. And so what this calculation showed us is however small the magnetoelastic interactions are, they play a role in affecting magnetization reversal. And one explanation towards why there's a minimum coercivity at 78.5% is the delicate balance between these material constants that's giving us the minimum hysteresis width at this composition. And that makes us rethink as to what if we change the geometry of the defect? What if we introduce multiple defects? Is this calculation going to change? And so we just did a test study where when we change, for example, the orientation of the defect, we changed the number of defects. We saw if we placed the defects close together. And the result was kind of surprising because what we noticed was, yes, the geometry of defects has subtle effects in which the magnetization reverses, and maybe especially if you zoom in, the curve of the shoulder of the hysteresis loop. But however, the effect was surprisingly small when compared to a more fundamental material constant. This was not as significant as it would be if I changed, for example, the combination of anisotropy and magnetostriction constants. And so this was a preliminary examination which kind of suggested that although defects may have effects, are surprisingly quite small, and the material constants are playing a more dominant role in this magnetization reversal. And it makes us rethink when you think of the alloy development strategy. Here is a plot which shows the range of anisotropy and magnetostriction constants that was explored by Bozorth and Walker back in the 1950s. And it shows this one alloy, one specific composition which has a value quite close to zero and extremely small magnetostriction values. They're of the order of 10⁻⁶ microstrains. And this is one specific alloy that gives you the smallest coercivity and makes us rethink, are we not examining the wider material parameter space? Because there could be several of these magnets in the wider material parameter space for delicate combinations of these magnetostriction and anisotropy values, but somehow our alloy development strategy is focused on making kappa 1 close to zero. I'll be missing out on several combinations of these constants where there could be other soft magnets with non-zero anisotropy values, which could be developed, but we're just not looking for them. So which is what motivated the last part of the work, which is what we call as the design of soft magnets. And so what we did was, in this work, we ran nearly 2,500 calculations wherein we systematically vary the material constants, kappa 1 and magnetostriction constant. The other constants are held, the other material parameters are held constant, just to kind of see the interplay between two material constants to start with. And so what you see is a result of the calculation of over 2,500 simulations. And the way you would read this plot is more like a heat map. And what that shows is that every specific combination of anisotropy constant and magnetostriction constant, there's a specific color. And that color represents what's the coercive field at this specific composition. So if I take an anisotropy constant, which is about 1,000 joules per meter cube over here, and I make the magnetostriction constant, let's say 0, I have a coercive force of about 15 orsteds or so. And so the region that you see in blue is the region that offers the smallest coercive field or the smallest coercivity, or these are the magnets that are softest with the smallest hysteresis width. And what you see here is a red dot that corresponds to that of a Permalloy composition, a value where the anisotropy is close to 0, but not exactly 0. And today's alloy development strategy is focused on making this anisotropy constant close to 0. And what our calculation in fact showed is, well, you can have a soft magnet with a non-zero anisotropy constant, say, for example, along this value over here. But if you tune your magnetostriction constant to suitable values, which is about 1,000 microstrains over here, you can actually get an alloy composition or a new magnetic alloy, which has coercive forces comparable to that of a Permalloy or soft magnets which kappa 1 close to 0. So what this essentially suggests or indicates is it produces a quadratic relation between your anisotropy constant and magnetostriction constant, wherein you can expand the alloy search strategy to not just focus on kappa 1 close to 0, but actually you can tune these constants to lie along this parabola and still develop a soft magnet. And the reason that this quadratic relationship, although we first discovered this by doing simulations, the reason that the theoretical explanation as to why this constant of the quadratic relation comes is if you go back to your micromagnetics energy, and you renormalize, you non-dimensionalize the different energy terms, and you measure which of these terms has the largest energy barrier just before your needle domain kind of grows abruptly, loses its stability and rotates, you see that the majority of the energy barrier is coming from the energy term controlled by this parameter. And so by minimizing this energy barrier, you can actually get the soft magnets to kind of rapidly switch from one direction to the other, not just for values where kappa 1 is close to 0, but also for other suitable values. And so this is one example where we have a quantitative design principle or a mathematical relationship for which you can reduce hysteresis, and potentially could be a guideline to search for new alloys. And what I'm doing together now with my student is we're actually looking at the interplay, not just between the one magnetostriction and kappa 1 constants, but also to look at the interplay, the presence of other magnetostriction constants. And rather than having a quadratic relation, we are constructing a three-dimensional surface. And if you have a soft magnetic alloy whose values are close enough to this surface, you can expect that this new alloy composition to have a small hysteresis as well. And that brings me to kind of to summarize the first line of work, when we showed about how these different material constants, or how a delicate interplay between different material constants can govern how some of these instabilities form. And the interplay between the two can, for example, be used to understand the origins of hysteresis, but as well used as a tool to calibrate the width of your hysteresis and identify combinations wherein you can minimize coercive forces in these soft magnets. And before I proceed to give an overview of the other work, I can take a pause and ask if there are any questions, or if you'd like me to share anything more in detail in this line of work. I'm very happy to do that. Okay, so I see no hands, and I'll give an overview of the second line of work, and we can take the Q&As together later. Okay, the second line of work is an ongoing line of research, and where we're interested to understand if we can crystallographically engineer magnetic materials to mitigate fatigue. And to introduce this line of work, it will be what I've done is a lot of this research draws inspiration from shape memory alloys. So I have a couple of slides to give a background as to where we're coming from and what I mean by crystallographic engineering. So if you take a shape memory alloy, these are structural materials that if you heat and cool this material across a Curie temperature, phase transformation temperature, you see an abrupt transformation of its unit lattices. Say, for example, from a cubic phase, it goes to that of a tetragonal symmetry. So you can have three different variants which during this transformation. And so what you see here on the left is a sketch of a shape memory alloy, which in its high temperature phase, like the austenite phase, has a cubic symmetry. And now if you cool the material, you're going to have the material transform, or these lattices transform to a tetragonal variant, for example, and each of them can transform independent of each other. So you can have different orientations of this lattice that nucleate in this material. So when they collectively form a microstructure, both of these phases coexist, and so they meet along a specific interface. And because these have different lattice geometries, this interface is going to be elastically stressed. So as a result, what they do is they orient their lattices to form what is called as a finely twinned microstructure. So they minimize the elastic stresses at this interface. And so the origin of microstructures in these shape memory alloys is associated with the fact that each of these lattices can fit together to form finely twinned microstructures. And this is something that you see when you look under a micrograph of a shape memory alloy. This is a uniform phase, which is the austenite phase, and a pretty sharp interface, this is the martensite phase, which is a lower symmetry phase, but essentially this phase has a fine mixture of twins. Now, every time you heat and cool this material, you have this interface that forms, or this martensite phase kind of grows, and when you cool the material, this phase grows, as this interface moves in this direction. When you heat it, the interface moves in this direction. Now, this interface, although it minimizes the stress, it's still elastically stressed. The stresses at this interface are not zero. And so every time you heat and cool this material, you have this elastically stressed interface that cycles through your material system, which is often associated with nucleating defects, is often associated with the fact that repeatedly stressing this material or heating and cooling this material is what contributes to fatigue. And so if you take an example, as other researchers have done, was if you take an example of a shape memory alloy made of titanium, nickel, and copper, And you cycle this material over 200 times. Here is an example where the phase transformation was induced by mechanical loads. And so this is your cycle 1, that's in black, and you cycle it repeatedly for 200 times. Your 200th stress strain cycle looks quite different from your first one, or in other words, the material develops fatigue. Now, if you go back to this microstructure and say, how you can I change the lattice geometries of the material so I can form an exactly compatible interface, or I eliminate the stresses at this interface, I can expect this material to cycle longer without developing fatigue. And that was what was a geometric constraint that was proposed recently in a recent work, which is called, which identifies a specific combination of lattice parameters. So they use that as a guide to change the composition of this alloy. So they changed the titanium, nickel, and copper in careful parts. So this new alloy satisfied the special lattice parameters necessary to eliminate the elastic stresses at that interface. And now they could cycle this material for over 200 times, and the fatigue that this material experienced before is pretty much eliminated, or is highly reduced in this example. And so this kind of inspires my work, in which you have these special combination of lattice parameters that can be used to eliminate fatigue in material. But now the question is, can we do a similar thing in case of magnetic materials? So, when you have in case of a shape memory alloy, material undergoes phase transformation from a cubic to a low symmetry phase. But in magnets, this phase transformation from the paramagnetic to the ferromagnetic phases is also accompanied by the presence of a spontaneous magnetic dipole. And this dipole can have 2 different crystallographic orientations. In this case, you can have 6 different tetragonal variants with different with magnetization along the opposite direction. And this paramagnetic to ferromagnetic phase transformation is not just accompanied by a structural distortion which satisfies different lattice geometries, but is also accompanied by new magnetic properties, the one that we discussed. Now the material has an anisotropy constant. You have magnetostriction constants, which is associated with the change in length when you go from the paramagnetic to a ferromagnetic phases. And we expect that these material constants are going to play an important role when you want to have a stress-free interface. So the line of work that we're doing at the moment is trying to understand the balance between these different material constants for which we can stabilize a stress-free interface that's not just stress-free, but also satisfies the magnetization compatibility of having divergence-free. So what I mean is, here's a microstructure of a nickel manganese gallium alloy, which forms a finely twinned martensite-like microstructure, except for the fact that this material is magnetized. So every time it forms this interface, it does not only have to satisfy minimum elastic energy conditions, but also needs to ensure that each of these variants that are magnetized satisfy a divergence-free condition so that they're not trapping certain magnetic monopoles inside the body. Where magnetic monopoles, for example, are very high energy states and are only observed in a theoretical framework. And so you need to ensure that your magnetization kind of flows smoothly around this interface and does not break any of the divergence-free conditions. And so that was the line of work which is something that we're looking at, and is a work that is being currently revised. But we identify a combination of a mathematical relationship between material constants. If one is to stabilize a highly reversible stress-free interface for which you can take the magnetic material between paramagnetic and ferromagnetic phases and you cycle them repeatedly and reversibly, one needs to ensure that that alloy has a combination of anisotropy constants that satisfy the constraint over here. So if you were to plot this on a plot with kappa 1 and kappa 2, which are your 2 anisotropy constants, if you want to tune a specific alloy which has ultra low fatigue, you would want to work in this region where your K1 is less than 0, but your K2 satisfies this constraint. And your magnetostriction constant needs to be an interplay between the 2 constants over here. So all of this calculation was done using a cubic lattice symmetry as the reference paramagnetic phase. And so your magnetostriction constants need to satisfy this delicate balance where lambda 111 is a negative of a third of the magnetostriction and the other constant. So for these values, we expect the material to form a stress-free interface. If one is looking to change the alloy composition to develop these alloys, this would, for example, be a guideline, a potential guideline to search for these alloys that can be transformed, or which are highly reversible and can be transformed from the paramagnetic to the ferromagnetic phases with minimum hysteresis loss. And with that, I'd like to thank my students, specifically Nega, as well as my previous mentor and collaborator, Dick James from the University of Minnesota. And I'm very happy, and thank you all very much for listening, and I'm very happy to take any questions. So,
Ananya, this is Prakash. So, Ananya,
hello, hi Prakash.
Hi. Yeah, very nice work on the nickel-ion system. I'm sure you know, but we do use nickel-ion as a seed layer in magnetic recording media, in perpendicular magnetic media, and we constantly optimize the properties and look at various aspects of it, magnetic, permeability, all this stuff, right? So to get a new perspective from some modelers. So my question is, do you collaborate with experimentalists on verifying some of these hypotheses and models?
Calculations? No, thank you very much for your kind words. And that is something that we're actually actively looking to collaborate. We have potentially a collaborator from Case Western, and but I'm happy to I'm open to other experimental collaborators as well, because what we right now have is a design principle, but what would naturally be a nice complementing fit, or something that can help verify or validate these predictions, would be to have some sort of experimentalist who could do this kind of combinatorial synthesis with different compositions. So you come closer to satisfying this design constraint. And if we can see any signatures that satisfy this design constraint reduces coercivity, that will be a very good affirmation of our results. So I'm very open to these collaborators. Yeah.
A follow-up thing on that. The seed in our media basically will also, you're looking at the properties of the seed nickel itself, but in the case of the media, it actually is a template for further growth of other alloys, the hexagonal HCP cobalt platinum alloys, ruthenium first, and then the hexagonal alloys, cobalt platinum based. And we are, the seed is actually a very important layer for us to control the grain size and the distribution. And we are constantly looking at ways to improve the processing, both from a magnetic, the response, as well as from a structural growth.
Mm-hmm.
So are you thinking on any work about how, for example, are you looking at any distributions within this layer and how they, correlate to the structure? The magnetic property, when I say distributions, I'm talking about even magnetic distributions in terms of, I guess it's easier if you're looking at hard magnets, looking at coercivity distributions and anisotropy distributions, but for a soft material like this, it's kind of pointless after a degree, right? So yeah, I just want to get your thoughts.
No, that's a very good question. So when you mention about distributions, one thing that comes to mind, please correct me if I'm wrong, is that of the grain sizes. The size of the grains in your polycrystalline material can greatly affect your coercive forces. And what I showed was how you can change a material constant to get soft magnets, but I'm aware of another active community wherein you change the grain size distributions to adjust your coercive force. You even make amorphous alloys. And so in the current mathematical framework that we have, we actually assume a single crystal, but there is a scope for investigating a variation of grain sizes grain topologies, the kind of the grain interfaces and distributions of those to see how that affects some of these magnetization reversal mechanisms, hysteresis width, or do we see a rapid change or rather a kind of a gradual change in this magnetization reversal? So those are aspects that we could see. But the way we started off with this work was motivated by the experimental investigation, and I guess I did not mention about that during my talk, is okay, the Permalloy was discovered in 1950s, but you have several groups since then who have reproduced this experimental results in maybe similar experimental conditions, but each time they generated a different microstructure. So each person who generated this bulk Permalloy generated a different microstructure, but somehow at this specific composition, you still saw the smallest coercivity. So while features like grain sizes and the kind of the presence or absence of these defects can affect coercive forces, we think there should be something more fundamental which is related to the composition in terms of material constants, for example, which play a dominant role. Was that something that you were getting at?
Yeah, I understand you're looking at a more fundamental aspect of materials rather than the growth and the materials part of it, right? Like, so yeah, I get it. Yeah, no worries.
Thank you. Yeah.
I'm just curious if you are able to validate some of these things experimentally. So that's the main thing.
Mm-hmm.
Okay. All right. Thank you so much. I appreciate it.
This is Roger Wood. I enjoyed your talk. Thank you. Question. I was very interested in the trade-off between anisotropy and the magnetostriction. And I just wondered to what extent are those adjustable separately? Do you have much freedom to control them separately, or is this just a theory?
Theory, yeah, no, that's a great question. That's something that I don't have a lot of insight into, because when we do these things, when we're scanning the parameter space in a theoretical framework, I can freely adjust. But it's a great question, because when I want to now dope the alloy or change the composition, if I change the anisotropy constant in the direction do I want, how much of freedom do I have in controlling how I want the magnetostriction to change? So that's something that I don't have much expertise on. But to that end, one other factor that one could think of when we're changing the alloy composition to see the interplay between these constants, and something that could perhaps be more under the control of an experimentalist, would be to introduce mechanical constraints. These could be, for example, growing the film on a substrate, so you can change the strains you impose on the material and shift your energy landscape in a way you want, the way the trade-off between your elastic energy and anisotropy to work. So while you may not be able to tune the fundamental material constant in a bulk alloy the way you could, one could take the assistance to start with one of these mechanical constraints. It could be substrate strains, it could be sort of applying a compressive load to make the magnetostriction or the elastic energy term behave in a way that kind of interplays with anisotropy for an easy magnetization reversal. But it's a good question. I don't know how you would tune them independently when you're just changing the composition of one alloy. Yeah.
Thank you.
Roger, nice to see you on video after a long time. You probably don't remember me, but we interfaced at WD before you left a couple of times.
Yes, I do indeed. It's nice to see several familiar faces, actually.
Thank you.
Including Tom.
Oh, Tao is here. Hi.
If I can ask a second question. Your answer there made me, or prompted another question, which was, what do you do about the boundary conditions in your simulation, both magnetic and mechanical?
Boundary conditions, yeah. So we're looking at a freestanding bulk alloy. So we're not introducing any mechanical constraints. We're allowing the strains to evolve naturally as the magnetization rotates. That is, we solve for this equilibrium conditions as the microstructure evolves, the stress conditions. The magnetic boundary conditions is imposed. So there are different kind of boundary conditions when we think of it in terms of the magnetic body. So one, of course, is because we introduce this defect at the geometric center. We need to satisfy the heterogeneous demagnetization field at the surfaces of these defects. So we ensure that it's a divergence-free condition just around the defect. And the second aspect of the magnetic boundary condition comes from the shape of the magnetic body. So in modeling the shape, what we do is we assume a flat, infinitely large ellipsoid, which is like a pancake, which means your magnetization is free to rotate in plane, but not out of plane. And the idea is this theoretically comes close to how experimentalists, when they measure these fundamental material constants, they make these disks. And so we assume a perfectly smooth interface. And so when I'm computing this magnetization reversal in this three-dimensional domain that I showed, it's actually embedded in one of these large ellipsoids. And I split the field so that there is a shape effect, or the shape anisotropy, or the demagnetization coming from the large shape, as well as the localized demagnetization that's coming from the defect in there. And so that's the kind of the boundary conditions that we use in this study.
Thank you. I understand. You did mention that. Yes.
Thank you.
I wanted to thank Professor Balakrishna very warmly for an illuminating lecture presented with great pedagogical skill. So thank you very, very much.